So welcome back again. So today's topic is the characteristic strength of material. It's a very important topic in considering the whole RCC because whatever things we are going to see in the coming modules or coming lectures will be based on the understanding of your thing on this characteristic of material. The first thing is the characteristic strength of concrete denoted by FCK. So now onwards it is actually the naming for the concrete. If you say the FCK is 20 Newton per mm square, it means the characteristic strength of the concrete is 20 Newton per mm square. If you say it is 25, FCK is 25, then it is 25 Newton per mm square. That is the concrete grade will be denoted by its characteristic strength. Okay. So what we do here is we'll be casting a 15 centimeter cube concrete. That is, the concrete will be having a size of 15 centimeter by 15 centimeter by 15 centimeter. The size of the concrete cube will be 15 centimeter cube. The concrete will be casted and it will be tested in a compression testing machine. It will be tested in a compression testing machine. That is, this will be conducted in the site as well. A minimum of 6 to 8 cubes will be taken in order to determine the characteristic strength. That is, I'll repeat once more, it is the strength of the concrete having dimension 15 by 15 by 15 centimeters, and the compression testing is being done. The minimum number of cubes required is what? Either the minimum number of cubes required is either 6 or 8. The minimum number of cube required is either 6 or 8. Now we'll discuss how we'll take the characteristic compressive strength. Suppose you are having 100 cubes. Which is having a dimension of 15 centimeter by 15 centimeter by 15 centimeter. And on the 28th day after you have casted, you will do the compression testing of these cubes. You'll have a proper curing of the 100 cubes. On the 28th day, what you will do? You will do the compression testing of these cubes, and at the time of casting, my required strength was 25 Newton per mm square. That is, I require a strength of 25 Newton per mm square. I have mixed design. I require a strength of 25 Newton per mm square. Okay, which means this 100 cubes should have a strength of minimum strength of what? 25 Newton per mm square. After 20 days I had done the compression testing, and if more than 95 of the cubes are having a strength more than 25 Newton per mm square, equal to or more than 25 Newton per mm square, I could say that the characteristic compressive strength of the concrete here is what? 25 Newton per mm square. That is, not more than 5% should be below what? 25 Newton per mm square. Then I could say the design compressive strength value is 25 MPa, or the characteristic compressive strength of this concrete is 25 Newton per mm square, or FCK is 25 Newton per mm square. You can see the definition for this. That is the characteristic strength of concrete. FCK is defined as the compressive strength of 150 mm cube, that is 15 centimeter cube, at the 28th day, expressed in Newton per mm square. Okay, Newton per mm square, below which not more than 5% of the test results are expected to fall. As you can see in clause number 6.1.1, it is written there clearly. That is, more than 95, that is not less than 5% of the tests are expected to fall. So here also you can see in table number 2, we had discussed this table number 2 in the previous classes. That is, based on the strength of the concrete is divided into ordinary concrete, standard concrete, and high strength concrete. Here I told you at the time what is the meaning of this 20. I'll tell in the later class. Now I hope you have understood that. Now summarizing this characteristic strength, I could say FCK indicates the compressive strength of concrete. It is a strength measured at the 28 days after casting, found by testing cubes of 150 mm by 150 mm by 150 mm in size. strength of the cubes may be or may not be same, because it depends on the amount of compaction, it depends on the amount of the material being used. It's manual process, so the strength of the concrete may not be same. If you have required a 25 Newton per mm square, you'll be having sometimes 26, you'll be having sometimes 27, you'll be having sometimes 24, you'll be having sometimes 30, but it should not be more, because we are doing the mix design. So it should not be there should not be a larger variation, but still there will be variation because of the manual compaction and all those things. Okay, and it's concrete, it won't be highly homogeneous as that of steel, so there will be a strength variation. In 95% cases, the result obtained should be that FC they should be greater than, here there is a thing, this should be greater than FCK value. Then I could say that the characteristic strength of the concrete is what, that much FCK. Okay, similar to characteristic strength of concrete, there is characteristic strength for steel also. Suppose I'm considering I am drawing the stress strain curve for HYSD bar. I'm drawing the stress strain curve for HYSD bars. I'll get a stress strain curve like this, which you will study later, and the yield stress corresponding to 0.00 0.002 strain 0.002 strain is called as the yield stress, or the stress corresponding to 0.002 strain is the yield stress. Suppose for a sample 1 I got the yield stress FYS 421 Newton per mm square. I got this sample. The yield stress as 421 Newton per mm square. Then I could say that for sample 1, the yield stress is what? Yield stress is 421 Newton per mm square. Now consider a group of samples. So sample 2 I got it as sample 2 I got it as 417 Newton per mm square. FYS 417 Newton per mm square. FYS 470 Newton per mm square. Then for sample 3 I got it as 412 Newton per mm square. 412 Newton per mm square. 412 Newton. For sample 4 I got it as 490 Newton per mm square. Like that it will go, 490 Newton per mm square. Similarly, I got it for 100 samples. I got values, somewhat random values like this. Okay, if I say for this sample, all the sample I have taken, if 95% more yield stress is greater than 95% more yield stress is 95% more yield stress is greater than 415 Newton per mm square, is greater than 450 Newton per mm square, then I could say that the characteristic strength of the steel is 415 Newton per mm square. It is similar to what your concrete itself. Then I could say here the characteristic strength of the steel used here is 415 Newton per mm square. That is 95% more of the sample should have an yield stress which is greater than 450 Newton per mm square. Then I could say that the characteristic strength of the material is what, or the steel is what, 450 Newton per mm square. And this stress strain curve for mild steel and HYSD bars this one you will study in the upcoming classes. Okay, fine. The next one is the characteristic load. It's seen in clause number 36.1 of IS 456/2000. It says that in limit state method, as I have explained in limit state method, we design for a particular load. That load has a chance in its lifetime that it won't occur. 95% chance that it won't occur. Only there is a chance of 5%, and that 5%, we may say that if that 5% load occurs, then there will be a total restriction, somewhat like that. So we will design the building for a load, and that value of load is, the specialty of that load is 95% chance that that load won't occur. So read the term characteristic load, clause number 36.2. The term characteristic load means that value of load which has a 95% probability of not being exceeded. See, this one is very important. That is 95% of not being exceeded during the lifetime of the structure. So you will design for a load that will not occur 95% of its lifetime, or 95% chance of not occurrence of that load is there, and that particular load is called as what? The characteristic load. And these are some of the extra things that you need to keep in your mind while designing. These things are required. That is, the first one is the tensile strength of concrete. Tensile strength of concrete. Even though we say that this concrete is very weak in tension, but still there is a minimum value of tensile force that the tensile stress uh, that the concrete can take, and that value is 0.7 root FCK. That is the flexural bending tensile strength of the concrete. That is 0.7 root FCK. So you need to by heart this value. This can be asked for your gate exams. It can be asked for your competitive exams and all. And the second one, that is the modulus of elasticity, that is given in clause number 6.2.3.1. It is EC, that is the short term elastic modulus, is 5000 root FCK. This also you need to understand. You need to by heart this value, 5000 root FCK. It is a short term elastic modulus. Okay, long term there will be effect of creep also. Now the code suggests certain design values for load as well as the material properties in order for a proper design or a safe design of the structure. This is given in page number 68 of your IS 456, clause number 36.3. If you see that, you can see the design values. So coming to the design values, the first one is the design strength of the material. I will be denoting it as FD. Design strength of the material I will be denoting as FD. Then it is obtained by dividing the characteristic strength by a partial safety factor for the material. That is, FD is equal to, if characteristic strength I am denoting by F, then it is obtained by dividing it by a partial safety factor gamma M, where gamma M is the partial safety factor for material, and it is 1.5 for concrete. It is 1.5 for concrete and 1.15 for steel. And you could see there is, for concrete it is a higher value. The partial safety factor is higher value. That is, the design strength that we are taking, will be somewhat lesser for concrete, since the denominator is having a higher value. It will be somewhat higher for steel. Can you tell what is the reason for that? It will be like since the concrete is made in site, there will be the quality assurance when compared to that of steel, which is made in factory, will be very much less. So we could say that the quality of the material will be very much there will be a lot of change in the quality of the material when compared with concrete and steel. The concrete being made in the site will depend on a lot of variables, lot of factors. As a result, we should give a more factor of safety, since there will be a lot of variance in the quality assured. But in case of steel, the quality is very much monitored, since it is made in a factory. So there won't be much issues in the case of the quality of the concrete. As a result, the factor of safety is very much small in case of steel when compared to concrete. You could see the strength is uniform for steel, so there is a smaller partial factor of safety taken when compared with concrete. Okay. Now the second one is the design load. The design value, first one was design strength for the material. Now the design load. So if I am denoting a design load as F small letter d, F small d, then the design loads are obtained by multiplying the characteristic load by the partial safety factor for load. That is, the design load are obtained by Fd is obtained by multiplying the characteristic load by a partial safety factor. I'll denote it as gamma F. I'll denote this partial safety factor gamma F, and the value for this gamma F is obtained from table number 18 of IS 456-2000. That is, the design load will be obtained by multiplying the characteristic load by its partial safety factor, and the partial safety factor is obtained from table number 18 of your IS 456, and it is shown like this. That is, if you are having dead load and induced load. Induced load is also called as IL. IL means induced load, or it is also called as live load. It is also called as live load. So if we are having a combination of, there is a load combination, means the load combination means the building will be acted upon by dead load, live load, earthquake load, wind load, isn't it? At a particular instant, it will be acted upon by different loads. So we will see the critical load combination. That is, whether the dead load and live load is causing higher damage, or whether it is a dead load and wind load causing, or whether it is a dead load or live load and wind load together causing, which is coming higher. We will go for that. Okay, the first one is the dead load plus live load combination is dead load plus live load. If you are considering only dead load plus live load, then the factor of safety taken is 1.5. That is, one load combination is I'll denote as C. So the first C1, I can say load combination C1 as what? 1.5 into dead load plus live load. I'll take it as 1.5 into dead load plus live load. Now the second load combination, if I'm considering it as, in the second load combination I'm considering C2 as, I will consider dead load and wind load. I will not consider the live load again. Then also the factor of safety is what? 1.5 into dead load plus wind load or earthquake load. We will not consider the wind load and earthquake load together. If we are considering wind load, then we will not consider earthquake load. It's because if we are designing the structure for earthquake load, wind load, dead load together, it's very uneconomical. That's why we will consider either wind load or earthquake load. Whichever is coming critical, we will consider that. And suppose I am considering together the three loads together, that is wind load, earthquake load, and wind load, dead load and live load, then I will consider the partial safety factor as 1.2, that is 1.2 into dead load plus live load plus wind load or earthquake load. This is because if I am taking 1.5, the section or the load will be very much high, and that load won't occur in the lifetime. So it's very much uneconomical for the structure to be constructed for such a very high load. It's very uneconomical to construct a structure for very high load, and that's why we consider, or the code gives the load factor or the partial safety factor as 1.2 when we are taking the case of dead load, induced load, and wind load. And here you can see a 0.9 here. That is we will reduce the dead load by a factor of 0.9 when we are considering retaining wall. When we are considering the stability of the retaining wall, the dead load will actually, the restoring force is provided by the dead load. So we will not consider the full amount of dead load. We will reduce the dead load, that you will study in detail when you are dealing with the design of retaining wall. Sorry. And in the case of limit state of serviceability, this is what I have said in the limit state of collapse, that limit state of tension, limit state of flexure, limit state of compression, those things we are considering the load combinations in this way. But when you are considering the limit state of serviceability, that is deflection, cracking, etc., we will not consider the load combination, or we will consider the load combination or the partial safety factors 1 itself. That is, we will not apply the load partial safety factor for loads when we are dealing with the limit state of serviceability. Okay. Now we will discuss the stress strain relationship for concrete. That is, when we do the compression testing of concrete, when we do the compression testing of the concrete in the lab and plot the stress strain variation, that is stress in the y-axis and strain in the x-axis, we will get a stress strain variation, that is, we will get a stress strain variation which is completely parabolic, okay. That is, we will get a stress strain relation which is completely parabolic. That is, we will get a actual curve of the stress, and we will get the actual curve of the stress in this form. We will get the actual curve of the stress in this form. That is, this is the actual curve. So you can see the actual curve is completely parabolic. But what we do is, we will after a strain of point 0.002, that is, after a strain of 0.002, we will assume that the concrete, or we will assume that the stress variation is linear. There is no further increase or decrease in the stress. We will consider that the stress variation is parabolic up to 0.002 strain, and after that it is linear, and the concrete will fail at a strain of 0.0035. The concrete will fail at a strain of 0.0025. Sorry, 0.0035. So this is very important. That is, it will be parabolic up to a strain of 0.002, and it will fail at a strain, and it is a straight portion, and it will fail at a strain of 0.0035. Now for the design purpose, we will idealize the stress strain curve for concrete. I told you it will be parabolic. It will be parabolic up to a strain of 0.002, and after that it's a straight line, and it will fail at a strain of 0.0035. So that value of the concrete is called as your characteristic compressive strength. That is your FCK. That is your FCK value. That value is called as your characteristic compressive strength, or your FCK value corresponding to your concrete. Okay, now I will divide. This curve is being obtained in the laboratory, right? When you test the concrete cube in the laboratory, you're getting this FCK value. That is your desired strength value. Now when you take it to the site, there are many uncertainties involved, right? There will be poor workmanship, there will be the mentality of the work, labor will be different, the material quality will be different, the batching is different. There will be a lot of uncertainties or variables associated when you are casting the same cube in the lab, as well as when you are casting the same cube in the field. So as a result, what we do is, we will decrease the strength, or material quantity, we will decrease it by a factor of 1.5. That is, we will consider the second curve. We will consider the second curve, that is having a value FCK divided by 1.5. FCK divided by 1.5. This is being considered to encounter the site variance between the laboratory and the site. That is the variation between the site and the laboratory. We will have a factor of 1.5, such that we will get a curve which is having 0.67 FCK. Now according to the limit state design, we will apply the factor of safety, that is your 1.5 for the material. That is, for concrete, the factor of safety is 1.5. We'll apply that factor of safety, and we will get the curve as 0.67 FCK divided by gamma m. That is 0.67 FCK divided by 1.5, and you will get this value as 0.446 FCK. That is the idealized stress strain curve. I'll take this curve 3 as my idealized stress strain curve for concrete, or the design curve for concrete. That is, this will be having a value, or the stress at the failure, that is 0.0035 strain, will be having a value of 0.00. Stress at this failure strain, that is 0.0035, will be having a value of 0.446 FCK. It will be having a value of 0.446 FCK. That is, if I summarize, for the purpose of design and for simplicity, the stress strain curve for concrete may be considered as a parabola, up to a strain of what, 0.002, and thereafter a straight line up to a point, or up to a strain of 0.0035, where the concrete is assumed to fail in flexure. So this is called as the idealized stress strain curve for concrete. That is, if I draw the idealized stress strain curve for concrete, I could say that if I draw the idealized stress strain curve for concrete, it will be a parabola up to, this is stress, this is strain, this will be a parabola up to a strain of 0.002, and after that it will be a straight line, it will be a straight line up to the strain of 0.0035, and this is the curve 1, and this value corresponds to your FCK. This value corresponds to your FCK. Now, in order to counter, or in order to take care of the field and the laboratory differences, what we do is we will divide it by a factor 1.5, or we will divide it by a factor 1.5, such that we will get a curve like this. We will get a curve 2, that is, this is FCK divided by 1.5, that is 0.67 FCK. Will get curve 2, that is 0.67 FCK. Now, to encounter or to consider the factor of safety associated with the material, that is for concrete it is 1.5, that is for concrete is 1.5, we will again divide this by a factor 1.5, sorry, this will again divide by a factor of 1.5, and we will get the curve 3, and that value is 0.446 FCK, and that value is 0.446 FCK. So you will see here this one, that is the first curve corresponds to your FCK value, characteristic strength, the idealized curve. Now, in order to take care of the field and the side variance, we will have the curve 2, that is 0.69 FCK. That is, you'll get by FCK divided by 1.5, you'll get as 0.69 FCK. And further, you will apply your factor of safety, that is 1.5 for concrete, and you will get this value, or you will get this curve. That is a design. This curve will be used for your design. That is the design curve, which is 0.002 up to 0.002 straight is parabolic. Then it will be a straight line, and at 0.0035 the concrete will fail in flexure, and this stress corresponding to that will be what, 0.446 FCK. So I could summarize it like this. That is, the curve 1 corresponds to the stress strain relation of a cube prepared and tested under laboratory condition. To get curve 2, a factor 0.67 is introduced to account for the difference in field and laboratory conditions. Okay. Further, a partial safety factor of material, that is 1.5, is introduced to get the curve 3, which is used as the design stress strain diagram for limit state design. That is, if I summarize, I could draw it. The design curve for concrete, I could write as stress strain. Design curve will be a parabola up to a strain of 0.002, and thereafter a straight line up to a strain of 0.0035, and this value of stress is 0.446 FCK. This value of stress is 0.446 FCK. Okay. Now, similar to that of concrete, you have idealized stress strain curve for mild steel also, as well as the edgewise bar. That is, we will draw the stress strain curve for your reinforcement. For that, what we do is we will do the tensile testing of the reinforcement. This you have studied in your last semester, first semester SM lab. You have done this, the tensile testing of your reinforcement, and here you will plot your strain in your y-axis and stress in your y-axis, and you will get a curve. You will get a curve that initially it is linearly varying, and after this it will be like this, and you will get a curve like this. Is it? So This is the lower yield point and this is the upper yield point. So the characteristic strength or the yield strength of the mild steel is taken as the lower yield point. The stress corresponding to lower yield point is taken as your yield strength of mild steel. And for the idealized stress strain curve, we will assume that after yield point there is no further increase in stress. That is, we will assume this is a straight line. There is no further increase in stress. We will assume this as a straight line, and this value of your stress is called as your Fy. This is called Fy, and that value for mild steel is 250 Newton 250 Newton per mm square. That value for your mild steel is 250 Newton per mm square. Now, according to IS 456-2000, you need to apply the factor of safety. Here, there is no difference between the field and laboratory because the steel is being made in the factory where there is enough quality control. So, just we need to apply the factor of safety for the material, and you know the factor of safety for the material we have discussed in the previous class. The factor of safety for the material, that is reinforcement, is what? 1.15. So we are applying the factor of safety for the material. We will get Fy divided by 1.15, that is, you will get it as 0.87 Fy. You will get the value as 0.87 Fy. That is the stress corresponding, or your design yield stress for your reinforcement. So you will get that value as 0.87 Fy. So if I plot that over here, you will get this value as 0.87 Fy. There will be somewhere here. It will go like this, and you will get this value as 0.87 Fy. So this value will be what? This value will be 0.87 Fy. Now, if you want to see the strain corresponding to your, or the strain at the time of your maximum yield stress or design yield stress, see, we will I told you that the stress strain curve for, you have seen in your SM lab, the stress strain curve for your mild steel will be linearly varying. That is, the initial modulus or the Young's modulus, I will get it from the curve here, right? The Young's modulus will be, since it is linearly varying, the Young's modulus is the initial tangent modulus, and here ES is what? ES is equal to 2 into 10 raised to 5 Newton per mm square. According to IS 456, we will take this value of Young's modulus of steel as 2 into 10 raised to 5 Newton per mm square. So we'll find out what is the strain corresponding to your design yield stress. You will find the strain corresponding to your 0.87 Fy. So you know that strain is equal to what? Strain is equal to, you'll take it as stress by Young's modulus, right? Stress by Young's modulus. So if I see here, the strain corresponding to this value, is this one, right? Strain corresponding to this value is this one. That is, I could write it as stress is what? What is the stress value? The stress value is what? 0.87 Fy, and the strain is, the Young's modulus is 2 into 10 raised to 5. So the strain is equal to what? 0.87 Fy. That is, Fy is 250 divided by 2 into 10 raised to 5. You will get this value as 0.00108. 0.00108. This value of strain, you will get this as 0.00108. So I could say the strain corresponding to 0.00108, the stress corresponding to 0.00108 strain is the yield stress for your, or design yield stress for your mild steel. So you need to have a clear understanding how this 0.00108 came, and this value for 0.875. So I'll explain you once more in detail. That is, we'll plot the stress strain curve. In that stress strain curve, we will assume that is the lower yield point is taken as the yield stress or the strength of the material for mild steel, since it is having a proper lower and upper yield point, and further a factor of safety for the material provided by IS 456-2000 is applied, such that we will get the design strength or design stress of the material as 0.87 Fy. Now, in order to find the value for your strain at your maximum stress level, we need to see the Young's modulus of your steel, that is 2 into 10 raised to 5. So the strain corresponding to your stress is stressed by Young's modulus, that is you will get the value as 0.00108. Similarly, you have the stress strain curve for your HYSD bar or the deformed bar, HYSD bar, or it is also called as deformed bars. So here when I am plotting and when I am doing the tensile test on your HYSD bar, when I am doing the tensile test on the HYSD bar, the stress is being plotted here, the stress in the y-axis and strain in the x-axis. When I am plotting the stress strain variation here, I'll not get a specific yield point or lower or upper yield point. I'll not get any lower or upper yield point. Instead of that, I'll be getting a curve like this. I'll be getting a curve like this. Okay, there is no specific, I told you there is no specific lower or upper yield point, and I told you in the beginning for HVSD bar it is having higher carbon content. As a result, as the carbon content increases, what will happen? As the carbon content increases, the strength increases, but the ductility decreases. So as the ductility decreases, which means what? The brittleness of the material will increase, and as a result there is no further deformation, or there is no formation of hinge. There will be sudden failure occurring for the material, and that's why you have seen there is no after this increase in stress, suddenly it breaks. So in order to find the yield stress, what we do is we will draw the initial tangent modulus of this material. We will draw the initial tangent modulus. Of the material, and at a strain of 0.002, we'll draw a curve which is parallel to your initial tangent modulus, which will meet at your curve at a point, and that value of stress is called as your proof stress. That value of stress is called as your proof stress. That is a stress corresponding to 0.002 strain is called as your proof stress. And we will assume that after this point there is no variation in stress, and the stress strain curve will be a straight line, and this value of your stress is your Fy, or yield stress for HYSD bars. So this value of stress is your yield stress for HYSD bars. That is a stress corresponding to 0.002 strain. Since you are not getting a definite yield point, lower yield point, we will take the stress corresponding to 0.002 strain, and that is your yield stress. Now further a factor of safety is applied. For reinforcement, it is 1.15. Further a factor of safety is applied. You'll get for reinforcement is 1.15. You'll get a curve like this. That is Fy divided by 1.15. You'll get 0.87 Fy. You'll get a curve like this, and this is your idealized stress strain curve for mild steel. That is, now we'll find out what is the strain corresponding to your yield stress. That is the strain corresponding to your maximum design stress. So this value, this is what? ES, that is your Young's modulus. Now we need to find out what is the strain corresponding to your yield stress. Okay, this is the value. We need to find out what is this value. So this value, if I'm taking it as x, up to here it is what? Up to here it is 0.002. So if I'm taking the value of this as x, I will get the value of x what? X is equal to what? That is the strain corresponding from, if I'm taking the similar triangles, I'm taking x is equal to what? That is the 0.87 Fy divided by ES, right? The strain corresponding to that value. So if I write the strain at the time when the steel reaches its maximum yield, I could write it as what? Strain is equal to what? 0.002, that is 0.002 plus x, that is 0.002 plus 0.87 Fy by ES. isn't it? That is the strain corresponding to, maximum yield stress for HYSD bar, and the strain corresponding to maximum yield stress for mild steel is 0.00108. Now we will have a small summary of what we have studied in the last 10 minutes. That is the stress strain curve for mild steel. That is, I will plot the stress in the y-axis and strain in the x-axis. The up to lower yield point, here you will see the lower yield point, we will have a linear variation. After that, the variation, we will not consider the variation, the stress will be constant, and we will apply a factor of safety of 1.15, and we will get this Fy divided by 1.15, that is 0.87 Fy, that is, we'll get this value as 0.87 Fy. We'll get this value as 0.87 Fy, and that is your design stress or design stress strain curve for concrete mild steel, and the strain corresponding to this is what? 0.00108. Similarly, you will have this stress strain curve for your deformed bars, that is your HYSD bars. Since this is not having a particular yield point, what we do is we will draw the line parallel to the initial tangent modulus at a strain corresponding to 0.002, and it will reach at a point, it will touch the point in the curve, and that is your proof stress, and the value of that proof stress is your corresponding yield strength or characteristic strength of the material for HYSD bars. Further, you will apply a factor of safety of 1.15, and you will get the value for your HYSD bars, yield strength of HYSD bars, design yield strength of HYSD bars as 0.87 Fy, and the strain corresponding to that value, you will get it as, corresponding to that value, you will get it as 0.002 plus 0.87 Fy by ES. So this is very important. You need to understand how you arrive into these values, that is values for your concrete, that is 0.446 FCK, similarly 0.00108 strain, 0.87 Fy, 0.002 plus 0.87 Fy by S. Those things you need to understand more clearly, then it will be easy for you in the upcoming lectures.